video, we are going to study the triangle group ABC again. It's under client name with the attribute Bootstrap. And I've also relabeled it. It's a copy. It's extracted from the other triangle group, which was called ABC. I've called this ABCBS for Bootstrap. And in it, there are two data sets of incremental triangles. The first one uses our exposure vector, base exposure, which this is workers' comp, so it reflects the wages bill for every accident year, the relative wages bill. And the other one is just the triangle without any exposures. And in the first instance, what we're going to do is create a bootstrap triangle of the original sample. In other words, we're going to reshuffle all these values, assign them to different accident years and development years to construct a bootstrap triangle. And a lot of you would argue this is pretty silly. And the reason it's pretty silly is because these values do not all come from the same distribution. And therefore, we're going to lose the structure that is actually inherent in the real data. So if I go back to my Bootstrap PowerPoint display, what we're essentially going to do is make all the fitted values 0. So if we make all the fitted values 0, then the data equals the residuals. And if we bootstrap the residuals, we create a bootstrap triangle of the residuals, we are creating a bootstrap triangle of the actual data. We're then going to take those bootstrap triangle or bootstrap residuals, add them to the fitted values, which are 0, to create the bootstrap triangle, which is the same as the bootstrap residuals. Well, let's do that. So what we'll do is we'll go into PTF, the probabilistic trend family modeling framework, where by default we've estimated the average development trend, calendar year trend, and the average level. And now we're going to set each parameter to 0. We can do that for the residual graph, the alpha to 0, and the iota to 0. And you can see that now all the fitted values are 0. Each parameter is 0. So this is really a graph of just the data, because if all the fitted values are 0, as we mentioned before, the data equals the residuals. If I save this model as 0 parameters, all the parameters has been set to 0. And now look at the data. A graph of the data, it should be the same as a graph of those residuals that represent the data. That graph is identical to this graph. Okay. So what we're going to do now, we've got the residuals, which actually on the log scale are in fact the data. We're going to put them all into a flask, so to speak. We're going to draw one at random, put it into that cell, put it back inside the flask, select another one at random, put it in that cell to create our bootstrap triangle of residuals or observations. In this case, they are the observations. So we go to Test, Simulate. Under the test option, simulate bootstrap triangles. Let's just simulate one. We then go back to the triangle group, right-click on the triangle group tab. We then go to data sets. There's the triangle that's just been created. Let's now call it from 0 parameters. Oops, let me escape. From 0 parameters. Para. Let's compare the two triangles. Open. Let's close this graph. Okay, so on the right we have the original data, the original triangle, and you can see that if you look at development year 0, the numbers by and large are increasing. But if you look at the Bootstrap sample of those values, you've got 496,000 and then a 35,000, and then you've got a 590,000 there. Now, where did this 590,000 come from? This 590,000 here, it was an observation that was sitting in development year 1 from there. Where did the 35,000 come from? Let's see, it must probably come from a development year. There it is, it's 35,000. So all we've really done is taken the real data, the numbers in these cells, and reshuffle them to create this Bootstrap triangle of the original data. Now, a lot of you would argue, well, that's very silly. And the reason, of course, it's silly is because you can't regard these values as all coming from the same distribution. Each one, in fact, comes from a different distribution. You'll see that once we design a model for it. So let's now take our model, which we've called 0 parameters, and copy it onto the Bootstrap sample and run it. And let's compare the two. So on the right is our data where we have fitted a 0 trend along the development years, 0 level, 0 calendar year trend. The same model applied, this is really the observed value now on the log scale of the Bootstrap triangle. You can see that the structure along the development years, in fact there's no structure, they're pretty by and large random. We've lost that structure because we have allocated some of these low values to early development years, some of these high values to these development years. So one would argue that's a silly thing to do. Well, and for that very reason, because this is very silly to do, if you have a model where the residuals have a lot of structure in them, and they're in fact not random when they're standardized, weighted standardized residuals are not random from one distribution, when you will create the Bootstrap sample of the residuals and then add them to the fitted values to create Bootstrap sample, a Bootstrap triangle, you'll find out that the structure in the original data is very different to the structure in the Bootstrap triangle, unless, of course, those residuals were random from the same distribution. Okay, so what we're going to do now is actually identify a model for the data, but then we're going to use the exposures. So let's close all the regression tables. Let's go back to the triangle group. Let's go to the PLI. PLI, in fact, has been adjusted by the exposures. Let's now just run the wizard to design a model, and you can see that there's a major calendar year shift. Along the calendar years, in the early calendar years, you have a trend of around 6% plus minus. In the last 2 calendar years, you have a huge trend of about 17% plus minus. And you might remember that an axiom is, one of the very important axioms that applies to any triangle, any incremental triangle, whether it's reported claims, closed claims, dollar paid losses, case reserve estimates, and that is that any calendar year trend projects in the other 2 directions. Let's see that this is actually true for this data. If we now plot the data on the log scale, you'll see that if you look at the trace for the accident year 1977, the numbers come down pretty fast, but in the last couple of development years, the decay is a bit low. It's not as strong because the 17% kicks in, and it's much larger than the calendar year trend of 7% in the early years. If you look at 1978, you'll see that it kicks in between development year 7 and 8. At 79, it kicks in 1 development year earlier. So as you go down the accident years, the kick-in of the 70% is always 1 development year earlier. That's That's the axiom, and it actually works for this data. That's what happens to this data. If we model the cumulative paid losses using the Mack method, so the base model, the starting model in the extended link ratio family is the Mack method. These are the volume-weighted averages, same as the Mack method. If you look at the residuals, you'll see that there's a major calendar year shift, but the Mack method overfits all the early calendar years and underfits this calendar years. In fact, if you do a forecast, you're really forecasting along the zero line in terms of future trend. If you do a forecast, you'll see that you underfit all these late calendar years, 90 versus 105, 168 versus 190, 335 versus 375, 548 versus 590, 425 versus 471, and so on. Some of you might like to calculate the volume-weighted averages or the Mack method just applied to the last 3 calendar years. Well, you still do not capture the calendar year trend structure, don't even capture this trend, but even if you did, there'd be no descriptors of it in the link ratios. Let's rerun the Mack method for all the data. Now, what would happen if you actually bootstrap these residuals? So what we would like to do, excuse me, we've applied the Mack method to some data. We have fitted values. We now have residuals, which do have structure in them. We're going to put all the residuals into a flask. We're going to choose one at random, put it into that cell, put it back into the flask because it's resampling with replacement. Choose another one at random, put it there, and so on. So in fact, what we're going to do is redistribute these residuals, shuffle them around. So it's likely to happen that some of these high residuals, these high positive residuals, might be shuffled into the early calendar years. These residuals will be shuffled into the last couple of calendar years, and therefore, in the bootstrap sample, we're going to create 3 of them. We're going to lose the structure that appears in the real data, which is inherent in the real data. So let's do that. 1, 2, 3. We've simulated 3. Did we save this as the Mack method? Let's save it. Although it's a default starting model in the extended link ratio family, but let's save it anyway. We go back to the triangle group. We've simulated 3 triangles, PLC, BS, BS1, BS2. The corresponding exposure has been assigned to them. We now go to PLC. We grab the Mack method and drop it on top of this triangle. The next one, the next bootstrap sample, BS1, BS2. Click here on the left and highlight the Mack method to each, well, we've already applied it to PLC. So BS, BS1, BS2. Highlight each of these. Now we want to run the Mack method on these 3 triangles, each one of these triangles. Click with the right button of your mouse, open. Now open all the residual displays with your right button of your mouse, select all, tile vertically, minimize other types, and let's see if any of them look like the real data. Well, you can see none of them do. This is the real data. It's now at the bottom right. With the real data, the Mack method, volume-weighted averages, overfit all these earlier calendar years, underfit. There's a strong trend here, which we found on the incremental data in the PTF modeling framework by designing a model. We used the wizard to design a model. You can see that these bootstrap samples do not have that structure. They look different. And good reason for that, because the method does not capture the calendar year trend structure. If I now close all this, I go back to my triangle group, I go to triangles, and I go to PLC BS and create the corresponding incremental triangle, but that was simulated for Mack. In other words, it's the incremental version of the cumulative triangle, bootstrap triangle that was simulated for Mack. I then go to data sets. I associate with that triangle the same exposure, base exposure. I now go to models. I go to the paid losses. I run my wizard models, say M6, they're all the same. I now am going to create 3 bootstrap samples from this model. Now this model does capture the trend structure. We're assuming that these residuals are random from the normal distribution. Do they come from a normal distribution? The answer is in the affirmative. Okay. Let's do that. So we go to test, simulate triangle. No, we don't simulate triangles, we simulate bootstrap triangles. Well, we'll reshuffle the residuals, 1, 2, 3. We'll do 3 of them. We'll go back to the triangle group. We're now going to copy the model M6 to BS1, which is our first simulated triangle using this PTF model. The one for Mack, simulated from a PTF model, simulated from a PTF model. Click on the left. Let's choose M6, BS1 for Mack, BS2, BS3. Right button of your mouse, open each. Tile vertically, minimize other types, so we just get the model displays for each. Tile vertically again. You can see this one has got a lot of parameters that you don't need. Well, that one was simulated for Mack. Now, with the right button of the mouse on model templates, select all, and we're going to estimate to each triangle what we call a statistical chain ladder model. It removes all development, it's only a diagnostic model, it removes all development year trends and accident year trends to see what's left over along the calendar years. So if we look at the residuals of all these, tile vertically, minimize other types, you can see that we remove, if you just look at this one for instance, you remove all development year trends and all accident year trends. That's why these residuals are always around 0, because between every 2 years you have another parameter. Between any 2 of these years you have a new parameter. Okay, now let's look at each one of these versus calendar year and see if you could spot the odd man out. Well, it's pretty obvious, the one at the bottom here. This one was simulated for Mack. It doesn't have the same calendar year structure. If we remove that one, very different, isn't it? That one is very different. Which is the real data? Let me try and see. This one is the real data. The one on the left there is the real data. These 3 here, 1, 2, 3, were simulated from the probabilistic trend family model, identified for the real data, and it seems to have the same kind of calendar year trends changing around the calendar year 84. This one is very different. If we now estimate the starting model, 1 parameter in each direction for each one of these triangles, can you tell which is the real data? Very hard to tell. That's the residuals versus calendar year. Let's look at them in 4 directions. Okay. Let's go back to the one generated by Mack. Where is that? This is the one generated by Mack, where the residuals look like that. Well, that one's the odd man out. This one here on the top left doesn't look like the others. Nothing like the others. Let's remove that one. For the others, we're going to run our model again, M6, 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 M6. So that's the 4. These are the 4 model displays. 3 are simulated, 1 is real. Let's look at the calendar year trends. Very similar trend structure, isn't it? Very similar estimates. What if we do a forecast for each? The answer statistically should be the same. Let's look at all the logbooks. Okay, let's pick the first one, which happens to be the real data. 7.266 plus minus 202. Is that the real data? No, it's not. Let me just check. No, this one was simulated. This is the real data. Check again. Yeah, PLI. That's the PLI. That's the real data. 7.1, the next one, simulated. 6.967, the answer is statistically all the same. It's very hard to tell which is the real data amongst those four triangles. Almost impossible to tell which is the real data and which three were simulated. So bootstrap samples that are created from the identified PTF model, the optimal model for the triangle, are indistinguishable from the real data. Yet bootstrap samples that you would have created using the Mack method are very different to the real data, both the cumulative and the incremental. And the main reason for that is when you estimate the Mack method to data that has calendar year trend changes, the method will not capture the calendar year trends. There will be that structure in the residuals. And even if there wasn't any structure, if you look at some of our other studies, if the trend along the calendar years was constant, and that is true for some data sets, the Mack method will capture that trend, but there's no descriptors of it in the method, and you won't know what it is. Before we just finish this particular video, just to show you something else, if I close all these regression tables, if I go back to the bootstrap sample of the original data where all the fitted values were 0, let's look at that. So we've got bootstrap sample with 0 parameters, go to PTF. Or in fact, why don't we run the 0 parameter model for the original data unadjusted for exposures and for the bootstrap sample from the original data. We bootstrap the original data. Open that. Look at the residuals again, and you'll see that they're very different. Doesn't make sense in just bootstrapping the triangle itself, because if you do that, you will assume that the observations all come from the same distribution. In the same way, it doesn't make sense to bootstrap residuals that have structure in them, because those residuals do not all come from the same distribution if you standardize them. Okay, if you look at the probability frequency plot of the bootstrap sample and the real data, they should be very similar. Except for the bootstrap sample, you can get repeated measurements because you are sampling with replacement. Okay, so I hope you have learned a lot by that, and there's much more interesting stuff to come. Thank you.